Okay, hello guys. Let me start today's class. This lecture video is make a lecture for last Wednesday canceled class. In the last session, we talked in detail about how context switching occurs in an operating system through the concept of limited direct execution. By the way, before performing context switching, there is something the operating system must do first. That is, it has to decide which process to run on the CPU next. This is called scheduling. So in today's class, we are going to talk about the basic concept of scheduling. And this is the list of contents for today's class. First, we will talk about the basics of scheduling. Then we will go over several performance metrics used in scheduling, followed by various scheduling algorithms. Lastly, we will discuss how scheduling should be handled when I/O operations are also taken into account. Before we get into scheduling, it's important to first understand the difference between mechanism and polish. These are two key aspects we always consider when designing computer systems. First, a mechanism refers to the low-level functionality of the system, that is, the components that provide the basic operations. In contrast, polish refers to high-level decision-making. It determines how those operations should be carried out. When a decision is made at the policy level, it gets applied to the mechanism, which then defines how the system behaves. To make this clear, we can think about building something with Lego blocks. Its individual Lego piece and the actions of stacking them together represent the mechanism. Then now, deciding what you want to build with those blocks, for example, whether you want to make a castle, a car, or something else, that decision-making process is the polish. So again, stacking the blocks is the mechanism, and choosing what to build is the polish. In the same way, context switching, which talked about last time, is the mechanism. It's the low-level operation the operating system used to switch between processes. But deciding which process to switch to and when the switch should happen, that's handled by scheduling. And this is called polish. So to redefine it, CPU scheduling is polish that decides which process to run next, given a set of processes that are in the ready state. In other words, it's about making a decision at the polish level to select the next process for execution. And basically, scheduling happens very frequently within a computer system. And because of that, it needs to be very fast in order to minimize performance overhead. That's why efficiency in scheduling is very important. If we go back to our earlier discussion about process abstraction, we talked about how one of the ready processes moves into the running state to execute on the CPU. And when the running process finishes its time slice, it moves back into the ready state, waiting for its next turn. Moreover, if the learning process encounters IO event and has to wait, it moves back into the blocked state. And once the IO operation completes, then this process transitions back to the ready state, where it waits again to be scheduled on the CPU. So The transition from the ready state to the learning state, that's what it called scheduling. And because this happens frequently, it's crucial that scheduling incurs as little overhead as possible. In other words, scheduling decisions needs to be made very quickly. Basically, scheduling can be performed in one of two approaches. One is called non-preemptive scheduling, and the other is preemptive scheduling. Last times I mentioned that context switching can happen in one of two ways: cooperative approach or non-cooperative approach. And depending on how context switching is handled, the type of scheduling used in the system is also determined. First, non-preemptive scheduling, the scheduler has to wait until the learning process voluntarily yields the CPU. That means the process finishes by itself first, and only after that does the scheduler do its job. This kind of scheduling is used in systems where context switching is cooperative. On the other hand, preemptive scheduling is possible in systems that support non-cooperative context switching. In this case, the scheduler doesn't have to wait for the process to yield. Instead, it can interrupt the process and forcibly take back the CPU. When it has control of the CPU, it can perform scheduling and trigger context switching immediately. This is what we call preemptive scheduling. Okay, then this time, let me introduce some terms related to scheduling. First, when we talk about scheduling, we often use the term workload. Workload refers to the set of jobs that the system needs to execute. Then, what exactly is job? You can think of a job as a process, and workload usually includes a description of each job. In other words, metadata about the job's behavior. For example, workload can specify the arrival time of job with status when the job enters the ready queue. And it can also include run time, that is, how long the job needs to run on the CPU. So workload is essentially a collection of jobs along with various details about how those jobs should be executed. And the scheduler is the logic that decides when each job should run on the CPU. And when you want to evaluate how good scheduling algorithm is, we use something called metrics. Metrics are criteria used to assess the quality of scheduling algorithm. I will explain more detail later, but this example includes turnaround time, response time, and fairness, and something like that. These metrics help us compare different algorithms and understand their strengths and weaknesses. Before we dive into different scheduling policies, let's first simplify our problem. We are going to make a few assumptions about the workload, that is, the set of jobs our system has to handle. These assumptions are not realistic, but they will help us build a clean starting point. First, we'll assume all jobs run for the same amount of time, and they all arrive at the same time. And when a job starts, it runs to completion. That is, there is no interrupt during job execution. Also, the jobs only use the CPU. In other words, we assume there is no I/O operation. And finally, we know in advance exactly how long each job will run on the CPU. That is, its runtime is already known. These assumptions are pretty strong, but don't worry, we will relax them one by one as we go. To evaluate how good or bad the scheduling policy is, we need some kind of measurement. One important metric is turnaround time. It's defined as the time a job finished minus the time it arrived. We assume all jobs arrive at the same time, and if the arrival time is 0, then the turnaround time is basically equal to the completion time of the job. This is the meaning of the turnaround time. And there is another metric to consider, which is fairness. This measures whether all jobs get a fair share of the CPU resource. But the problem is that performance and fairness often conflict each other. I mean, a policy that's great for performance might be terrible for fairness, and vice versa. So that's one of the central challenges in scheduling. But in today's class, we will focus on only performance metrics, that is turnaround time, and fairness will be handled later again. Then next, let's look at the simplest scheduling algorithm, first in, first out, which is also called FIFO. And it is also called FCFS, which stands for first come, first served. This is because that this is just like waiting in line at a bank or fast food counter. That is, in this environment, the first person to arrive is served first. Like this way, in computer systems, FIFO follows the same rule. That is, the first job to arrive is the first to run on the CPU. And this scheduling is non-preemptive, which means its task runs to completion without any interrupt. And one nice thing about FIFO is that it's easy to implement, and it can avoid a problem called starvation. Starvation happens when a job waits forever because other jobs keep getting scheduled ahead of it. But in FIFO, once a job is in line, it will eventually run. This means that no job gets skipped or pushed back, so starvation doesn't occur in this algorithm. Let's look at this example. We assume there are 3 jobs, A, B, and C. And they all arrive at the same time, that is time 0. But due to tiny time differences, A enters the ready queue just before B, and B just before C. And we assume each job runs for 10 seconds, so FIFO will run A first, and then B, and then C. Then their turnaround times will be 10, 20, and 13 seconds respectively. So the average turnaround time is 20 seconds by this formula. It's simple, fair in a basic sense, and ensures progress, but as we'll see next, it has some problems too. Even though FIFO is simple and fair in some ways, it doesn't always perform well. Now let's relax our first assumption, which is that all jobs run for the same amount of time. Then what happens if job lengths vary? Okay, let's see this example. In this example, jobs A, B, and C arrive at the same time, And just like previous example, A enters the ready queue first, followed by B and then C. But this time A runs for 100 seconds, while B and C only needs 10 seconds each. And FIFO sticks to a live order, so the scheduler runs job A first. This means B and C have to wait a long time before they even get to start. Then what are their turnaround times? As you can see, A finishes at 100 and B at 110 and C at 120. Then this means the average turnaround time is 110 seconds by this formula, right? And this situation is called convoy effect. In this problem, a long job at the front holds up all the shorter jobs behind it, dragging down overall performance. So, in real systems, this can lead to poor responsiveness and inefficient CPU use, especially if many small, interactive jobs are stuck behind big ones. To solve the convoy effect problem, we need smarter scheduling strategies. And one simple but powerful idea is shortest job first. It is also called SJF. As the name suggests, this policy always runs the job with the shortest runtime first. Then it picks the next shortest job and so on. And basically SJF is a non-preemptive scheduler, meaning once a job starts, it runs to completion. Okay, then let's revisit our earlier example. That is, there are 3 jobs, A, B, and C, and they are alive at the same time. And A needs 100 seconds, while B and C only need 10 seconds each. And with SJF, the scheduler runs B and C first, and then A, because B and C have a shorter runtime than job A. And when 2 jobs have the same runtime, like B and C, SJF breaks the tie using a live order. So B will be scheduled first in this example. This means B finishes at 10, C at 20, and A at 120. So the average turnaround time is now just 15 seconds, much better than 110 seconds we got with FIFO. So this clearly shows how choosing the right job order can make a huge difference in performance. In fact, under our current assumptions, SJF gives us the optimal turnaround time. Okay, then now let's make our model a little more realistic by relaxing the second assumption, which is that all jobs are live at the same time. In real system, jobs are live at different times. Then what happens to SJF in that case? Let's consider this example. Job A arrives at time 0 and it needs 100 seconds to run. And jobs B and C arrive at time 10 and each of them needs only 10 seconds. Because SJF is non-preemptive, when A starts running at time 0, it keeps the CPU until it finishes. This means B and C have to wait the full 100 seconds before they even get a chance. So as a result, B finishes at 110 and C finishes at 120 seconds. then the average turnaround times become much worse. I mean, a turnaround times is 100, and B is also 100 because its arrival time is 10. And like this, C's turnaround time is 110 because its arrival time is also 10. Then, as a result, the average turnaround time is 103.33 seconds. So, even though B and C are short jobs, SJF didn't help them here because it didn't consider their late arrival. So, while SJF works well when all jobs are present from the beginning, it performs poorly when new shorter jobs arrive after long one has already started. To fix the problem, we need a scheduler that can react when shorter jobs arrive, even if long job is already running. To do that, we now relax assumption 3, which is that each job runs to completion once started. This means we allow preemptive scheduling. The new algorithm is called shortest time to completion first, which is also called STCF. And it is also known as PSJF or SRTF. Okay, basically, STCF works like SJF, but with one important difference. That is, it allows preemption. So you can consider STCF is like a preemptive version of SJF. In this algorithm, if a new job arrives with shorter remaining time than currently running job, the scheduler interrupts the current job and switches to the shorter jobs. Okay, then let's go back to our example. Job A arrives at time 10 and needs 100 seconds. And jobs B and C arrive later at time 10 and needs 10 seconds each. With STCF algorithm, A begins running at time 0, but at time 10, when B and C arrive, the scheduler checks which job has the shortest remaining time. At this point, B and C only need 10 seconds, and A still has 19 seconds left. So STCF will pause the job A and run job B first and then C. And when they are done, job A can resume and run to completion, like this example. So the turnaround times are much better. I mean, job B finishes at 20, C at 30, and job A at 120. So A's turnaround time is 120, B is 10, and C is 20. As a result, the average turnaround time is 50 seconds, which is a big improvement over SJF in this case. So, by relaxing assumption 3 and allowing preemption, we get smarter and more flexible scheduling polish. So far, we've talked about turnaround time, which means how long it takes for a job to complete after it arrives. But in many systems, especially interactive ones, users care more about how quickly the system responds. That leads us to a new metric, which is response time. Response time is defined as the time between when a job arrives and when it gets scheduled on the CPU for the first time. And here's the formula. response time can be calculated by the arrival time from the time of the first CPU execution. While STCF is excellent at minimizing turnaround time, it's not always ideal for response time. In certain scenarios, especially when multiple jobs compete for the CPU, some jobs may have to wait a while before they even get a chance to run. Imagine you're watching a long movie on your computer and then you try to open a word processor to type something. Under STCF, if the movie is running and still has the shortest remaining time, your word process will not even start until the movie finishes. This is obviously not acceptable in an interactive system. Then, how can you build a scheduler that is sensitive to response time? So, to address the response time problem, especially in interactive systems, we introduced a new scheduling algorithm, which is round robin. And basically, this is the fundamental scheduling algorithm in time-sharing systems. Its key idea is very simple. Instead of running each job to completion, the scheduler gives each job a fixed time slice, which is also called scheduling quantum. And then the scheduler runs a job for one time slice, then moves on to the next job in the ready queue, and so on, cycling through all jobs repeatedly until they finish. So this approach ensures that every job gets CPU time quickly, making it ideal for interactive systems. And the ready queue in round robin is usually managed as a circular FIFO queue. That is first in, first out, and left around. So we can say round robin is preemptive by design. And one important detail is that the length of time slice must be a multiple of the time interrupt period, because the operating system can take control of the CPU whenever a timer interrupt occurs. So with round robin, no job can monopolize the CPU, and there is no starvation. It's very fair polish, and this fairness leads to good response time, especially when jobs are short or interactive. Okay, then now let's compare how SJF and round robin perform using the same workload. I suppose we have three jobs, A, B, and C, and they all arrive at the same time. And each job requires 5 seconds of CPU time. Then let's start with SJF. Since all jobs are the same length, the scheduler just picks one, say A, and runs it to completion. And then the scheduler runs job B and then C. Then what happens? A starts immediately and finishes at time 5, and B starts at here and finishes at time 10, and C starts at here and finishes at time 15. So in terms of response time, A has 0 seconds because it started immediately, and B has 5 seconds because it arrived at time 0 and it started using CPU at time 5. In the same way, C has response time of 10 because it arrived at time 0 and it started using CPU at time 10, right? So the average response time is 5 seconds. And what is turnaround time? In terms of turnaround time, A is 5 seconds, B is 10, and C is 15, so the average is 10 seconds. Okay? Okay, then now let's see what happens with round robin using a time slice of 1 second, like this figure. So the CPU switches between the 3 jobs every second, A, B, C, A, B, C, and so on, until they all finish. This means A starts at time 0, B at 1, and C at 2. So their response times are 0, 1, and 2, respectively, and the average response time is just 1 second, much better than SJF. But they all take longer to finish. A finishes at time 13, B at 14, and C at 15. That gives us average turnaround time of 14 seconds, worse than SJF. Then what's the takeaway? Round robin gives us a much better response time, which makes the system feel more responsive and interactive. But SJF gives us better turnaround time, meaning that on average jobs complete earlier. This illustrates the classic trade-off. A scheduler that improves response time often hurt overall turnaround time and vice versa. This means you cannot always optimize both things at the same time. Okay, then let's take a closer look at round robin and talk about key parameter, which is the length of the time slice. If the time slice is too short, the system feels very responsive, but the downside is frequent context switching, which causes overhead and wastes CPU time. If the time slice is too long, we can reduce the overhead of context switching, but now jobs have to wait longer for their turn. This means it has very low response time, especially for short or interactive jobs. So there is a trade-off for the length of the time slice. Short time slices can improve the responsiveness, but long time slices can improve efficiency. So a well-chosen time slice strikes a balance between these two factors. But if the time slice is poorly chosen, either responsiveness or efficiency will suffer. So far, we've assumed that all jobs only use the CPU. That is, there are no I/O operations. This is our first assumption. But that's clearly not realistic because most real programs perform I/O operation. And when a job performs I/O, it cannot use the CPU, which means it's blocked and waiting for the I/O to complete. At that point, the scheduler should pick another job that's ready to run, instead of leaving the CPU idle. Then, when the I/O completes, the operating system gets interrupted, and the job moves from the blocked state back to the ready queue. This means a scheduler should be I/O aware. That is, it shouldn't waste time waiting for a blocked job, and it should quickly switch to another runnable job. By doing so, we can keep the CPU busy while other jobs are waiting on I/O operations. Okay, then let's see how I/O affects scheduling with a concrete example. We have two jobs, A and B, and both require 50 milliseconds of CPU time in total. But they behave differently. Job A runs for 10 milliseconds and then performs I/O operation that takes 10 milliseconds. It does this 5 times, alternating between CPU and I/O. On the other hand, job B just use the CPU for 50 milliseconds straight with no I/O operation at all. Now I suppose that a scheduler learns A first and then learns B. Okay, then let's take a look at how the system behaves when you use STCF scheduler. In this example, the scheduler always picks the job with the shortest remaining time. And this figure shows two different scenarios using the same jobs, A and B. First, in the top timeline, the scheduler is not I/O aware. I mean, it loads A first, but when A issues I/O request, the CPU just waits at this point, because the remaining time of A is 40 milliseconds, summing up this segment, this of jobs. It is less than B's remaining time of 50 milliseconds. So at this point, CPU waits until A becomes ready again. And job B doesn't get scheduled until A finishes all of its execution according to STCF. So in this scenario, as you can see, we have many idle CPU time like this, okay? Which is very inefficient. Now, look at the bottom timeline. This is what happens when you use I/O-aware STCF scheduler. Basically, this scheduler handles its 10 milliseconds of jobs as an independent job. So, whenever A becomes ready after I/O, it looks like a new short job. And its remaining time is smaller than B's remaining time, so STCF picks this subjob at this point. So the result is this alternating pattern. I mean, A runs for 10 milliseconds, then performs I/O, and while A is waiting, B runs on the CPU. And the job A returns to the ready queue, then it preempts B at this point. Because the schedule regards this subjob as an independent job with the remaining time 10 milliseconds. So this creates overlap. A used the disk while B used the CPU. As a result, the CPU stays busy almost the entire time, maximizing resource utilization. So, by treating short units of CPU work as separate jobs, I/O-aware STCF scheduler can make better scheduling decisions in this scenario. Okay, then this slide shows what I've explained in the previous slide. When a job performs I/O request, it can't use the CPU. So it moves from the running state to the blocked state. Then the scheduler picks another job from the ready queue to keep the CPU busy. And once I/O completes, the device sends an interrupt signal to CPU. Then the operating system handles it and moves the job back to the ready state. And at that point, the scheduler may choose to run it again, possibly preempting the current job. Thus, this event-driven behavior allows the system to overlap I/O and CPU use efficiently, keeping performance high and the system responsive. Okay, then that's all for today's class. If you have any question for this lecture, please leave me a message in our Slack channel or LMS system. Then we will see you next Monday. Thank you for your attention.